Okay, so this lecture is going to be over dependent events. Remember, a dependent event relies on something else. So you depend on someone else. The dependence event depends on what happens in the first selection. So I'm on page 778 in our books doing example 3. So there are 4 oranges, 7 bananas, and 5 apples in a fruit basket. Ignacio selects a piece of fruit at random, and then Terrence selects a piece of fruit at random. We need to find the probability that 2 apples are chosen. The reason why this is a dependent event is because it depends. If I pick out an apple the first time, I don't have as many apples in my fruit basket because I ate that one. I also don't have as many fruit in my fruit basket to choose from. So it depends on what you get the first time of the probability of the second one. So we're still going to take our event 1 and multiply it times our event 2. So event 1, we want to know the probability that 2 apples are chosen. So you can see in my fruit basket over here that I have 1, 2, 3, 4, 5 apples out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 total fruits in my basket. Another way of doing that was you could have taken 4 plus 7, which is 11, and then add 5, which gives you your total amount of fruit in your basket, which is 16. Okay? My event 2. If I selected an apple the first time, that guy is no longer in there. So now I have 1, 2, 3, 4 apples out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 fruit. So now I can just multiply. 5 times 4 is 20. 16 times 15 is 240. I can reduce this by crossing off my zeros and then simplifying it again by dividing the top and bottom by 2. 2 divided by 2 is 1. 24 divided by 2 is 12. I can then calculate the decimal by taking 1 divided by 12. I get 0.808, which is 8%. Okay? Another way of thinking about this, instead of counting my fruit in my basket, if I have 5 apples to start with and 16 total fruit, if I take 1 out, I'm left with 4 apples and only 15 fruit because I subtracted 1. I took 1 out. So that's another way of thinking it if you didn't draw it out. I am going to do another example of a dependent event. This one is not in your book, so you might want to write it down as I go through it. Again, remember, you can always pause this video if I'm going too fast, and then start it up again when you're ready. Okay, so this problem, there are 4 red, 8 yellow, and 6 blue socks mixed up in a drawer. Once a sock is selected, it's not replaced. Find the probability of reaching in to the drawer without looking and choosing 2 blue socks. The key word in this story problem is not replace. So I'm not putting my socks back into the drawer. I'm taking 1 out and I'm leaving it out. So I have 4 red, 8 yellow, 6 blue. So how many total socks do you have in this drawer? Well, 4 plus 8 is 12, plus 6 more would be 18. So I have 18 total socks. Okay. I want to know the probability of choosing 2 blue socks. So I have 6 blue socks when I start, 6 out of the 18, times, if I took out one of those blue socks, I'm left with 5 blue socks. And since I took 1 out, I only have 17 in the drawer. So again, this is a dependent event because I changed the probability of the second one based on what I got the first time. So 6 times 5 is 30. 18 times 17 is 306. This can be reduced by 6 on top and bottom, I get 5 on top, 51 on bottom. I can then type in 5 divided by 51 into my calculator, and I get 0.10 when I round to the nearest 10, which makes that 10%. So that is the probability of reaching into the drawer without looking and choosing 2 blue socks. I am going to go over the problems on page 778, number 1 through 3, just to give you some more examples on how we're calculating independent and dependent events. If you want to follow along and do them, you can. If you think that you've got it, you can go ahead and get started on your assignment. So on number 1, it says a penny is tossed and a number cube is rolled. Find the probability of each. So we need to figure out the probability of landing on tails and 3, rolling at 3. So when you have a penny, you have 2 total options, heads or tails. However, only one of those options are tails, which is what we want. So favorable over total. So our favorable, there's only 1 tails, 2, there's 2 total options on our penny. Times a 3. Probability of rolling a 3. Now our penny doesn't affect our cube, so it doesn't matter. On a dice you have 6 total options, but only one of those options are 3. 1 times 1 is 1, 2 times 6 is 12. So my answer for 1 would be 1/12, which 1 divided by 12 as a decimal is 0.08, which is also 8%. Okay, number 2, probability of heads and an odd number. Remember, we're always going to do our favorable over our total. So my favorable, I have 1 option that is heads out of 2 options on my penny, heads or tails. Times, on a dice, you have the options of 1, 2, 3, 4, 5, or 6. So I have 6 total options. And I have 3 options that are odd. So 1 times 3 is 3, and 2 times 6 is 12. I can then reduce this into 1/4, which as a decimal is 0.25 and 25%. Number 3, cards are labeled 5, 6, 7, 8, and 9. Are in a stack. A card is drawn and not replaced. Then a second card is drawn at random. Find the probability of drawing 2 even numbers. So this is dependent because I'm picking out a card and I'm not putting it back in, so that changes my probability. So the first one, I need 2 even numbers. So for even numbers up here, I have 6 and 8. So I have 2 out of 1, 2, 3, 4, 5 total options. Times. Now I took out one of those even numbers. So if I took out a 6, let's say, I only have 1 option left. But I have 1, 2, 3, 4 cards left. So now I can calculate 2 times 1 is 2, 5 times 4 is 20. You can divide the top and bottom by 2 to get 1/10, which is 0.1 as a decimal, or 10%. This one was a dependent event.